Recording. Good evening, everybody. This is One Tug, so if you weren't here for the One Tug event, you're in the wrong place. Our guest this evening is Sean Kileen. Is that how it's pronounced?
Kileen.
Kileen. Okay.
But yeah, pretty darn close. So we'll take it.
So that's that. Let me see. Get the next slide. Pardon me. By attending this meeting, you are agreeing to be recorded. So we are recording this. And it will be posted after Santosh puts it up to YouTube. When you're not talking, please mute. If you have questions, like I guess we all know what Teams is now, and where to raise your hand. So if you have any questions, please raise your hand. Tonight's talk is about Akka, an actor model framework. I'm anxious to hear about this. This is your the board here at One Tug. Santosh is on the line. Tim is on the line. I'm on the line. Haven't seen Andy this evening. I think he had a prior commitment. These are the best ways to reach us. Pretty much Twitter and Meetup. Meetup's the best place to find out when our events are going to be. Let me see here. We have an upcoming meeting in August for Siva. It's going to do GitOps. That's on August 12th. We have no sponsors this month, so as always, Santosh, if you do want to sponsor, definitely hit us up on board at onetug.net. Want to open it? Does anybody have any announcements? Anything they want to promote?
Yeah, I have an announcement. So there is an opportunity for remote .NET developers to an acquaintance of mine. If you're interested, just ping me. It's a kind of a mid-senior to senior level. So that's the level of experience they're looking for. So if you have that, just reach out to me, and I will be happy to put you in touch for the job opportunity.
Santosh, why don't you put your email or your contact info in the chat?
Yes, thank you for that. I will do that right now.
All right. Any more announcements? All right. Well, with no further ado, we're going to introduce Sean. He's got 15 years of experience. He's currently the technical director at Cat Tech Consulting in the DC area. When you see in real life, you can find me enjoying a new dad. Nice. Sipping a great beer. I plan on sipping a beer as soon as I hide myself. I like that. So anyway, without any further ado, here's Sean. Sean, I'm going to stop sharing, and it's your go.
That sounds great. Hi, everybody. I hope you're doing as well as can be these days. I know we've been all cooped up for a bit, but I'm happy to be on the other side of a webcam with you. I'll go ahead and share my screen, and we can go ahead and kick this off. All right. You should be seeing the screen. If you can't see it, let me know. Otherwise, we'll go from there. So again, happy to be here. Hope to be in person with you all at some point soon. But one of the nice things about this is getting to virtually visit sunny Florida, even if I can't be there. I've been there a few times for events like Code on the Beach and so forth, and really looking forward to getting back sometime in the future. But we're here today to talk about Akka.NET and the actor model and an introduction to that. And so let's go ahead and we'll dive in. We'll talk a little bit about what we're going to cover today, a big part of which is going to hopefully be demos. I also want to mention before I get into this presentation that I absolutely love feedback. So in addition to the questions that I hope you'll be posting in the chat throughout the talk this evening, I also really appreciate feedback if the demos are unclear. If you think there's a better concept that I could use to illustrate something, if some part of this presentation didn't really click with you, I'd love to hear that, because I'm currently working on the next iteration of it, and what your feedback is going to do is going to help me tune that to make it more effective for anybody else. So really appreciate any feedback that you've got. Certainly, afterwards or during, if you're brave enough, feel free to drop it in the chat, and I promise I will take it the best I can. No. So today we're going to cover, we're going to talk a little bit about why all this matters, why the reactive manifesto, why reactive applications, where Akka.NET fits in the picture of that application. the history and overview of the actor model and Akka.NET. Not too much. We're going to keep it pretty high level, pretty light. We're going to try to go a little heavier on the concepts of the actor model and the benefits of the actor model. And I've saved a big chunk of space this evening for demos to try to show and illustrate some of the actor model's concepts. All right. So to kick this off, before I start talking about this, one of the folks I'd like to highlight and thank is Roger Johansson, one of the big contributors to the Akka.NET project. He also is currently maintains the Proto-Actor project, which is another actor model project written in C# and Go. I give special thanks here to Roger because the graphics that I'm going to use tonight, if you see a graphic that is even remotely well polished, that would be Roger's work. And Roger has graciously agreed to allow me to use his graphics, and so I always make sure to give him a shout out. You can find him in these places, and certainly he is someone to look out for and to watch in the actor space if you're interested in things. So I also like to point out that Roger, like anybody else, gets confused by things sometimes, and so whenever I highlight someone who's a sort of what I consider a luminary in the space, I also try to highlight a spot where they feel like a beginner, because we're all beginners at something here. And one of the things that we're going to talk about tonight is the actor model is a new paradigm. It's a new way of thinking about how we approach programming if you are currently used to the object-oriented model of programming. And so when you think about that paradigm shift, we're all going to feel a bit like a beginner. It's a bit out of our comfort zone. This is just a nice reminder that Roger, too, occasionally feels a bit out of his comfort zone. And I think it's important to highlight that for those of us who may be newer to these concepts. I also like to give a big shout out to a group called Petabridge. Petabridge is a company founded by Aaron Steinert, who's one of the current maintainer of Akka.NET. Petabridge does a ton of work with Akka.NET, and they build consulting services on top of that. They've got some paid product offerings that go along with that. But one of the reasons I like to shout out Petabridge the most is they put together some phenomenal documentation and introductory documentation on their website. One of my favorite pieces of reference materials there is the Akka.NET Bootcamp that they put out. Sort of sends you like a drip email every couple of days with some introductory information, builds on the concepts before it. Very helpful for those getting started. So really recommend checking that out. I think it's very important. I also like to give a shout out to the .NET Foundation, because if you haven't heard of the .NET Foundation, it is, I'm going to call it the little engine that could of open source foundations. It's really trying to make an impact on the .NET open source world. You can become a member of the .NET Foundation if you meet certain requirements, and they try to keep the bar reasonably passable for those of you who may be on the fence about joining. Highly recommend checking them out, getting involved. They have great ways to get back to the community and to think about getting further involved in .NET's open source future. Also, right now, I believe they have elections going on, or they're seeking nominations for their next round of board of directors elections. So if you know someone who would be a good candidate to sit on the board of directors for the .NET Foundation, or if you yourself are interested in running, I highly recommend you checking that out. In addition to this, if you have a company that wants to invest in the future of .NET's open source ecosystem, because many of your company's supply chains probably depend on some sort of .NET open source technology. If that's the case, your companies can also sponsor the .NET Foundation as a corporate sponsor, which goes a long way to providing dues and goes a long way to providing funds for programs and initiatives that the foundation wants to undertake. So that's my spiel there. I am not on the board of directors of the .NET Foundation, but I am happily a member, and I think it could be an important organization to give back to the community. All right, I'm Sean. This is probably the least interesting slide on the entire presentation. My contact information will be down at the bottom throughout the slideshow, and we'll make sure that you have my contact information at the end. As we mentioned in the intro, I currently am a technical director at CapTech Consulting, so feel free to give them a look when you have a minute. So let's talk a little bit about why the reactive matter, or why the actor model, why reactive applications matter, why this talk matters, really why any of this presentation matters. A lot of our applications previously, or perhaps even still today, are built on a sort of request and response model, right? Most HTTP applications, you send a request up, you get a response back. And this is okay to a certain extent, and for certain workloads it may be, but our users have moved beyond that, right? Our users expect real time. Our users expect applications to be fault tolerant. Our users expect our applications to perform well under all kinds of pressure. Our users expect our applications to perform well whether they are using it along a ton of other people or whether they're using it with a handful of people. And so I think that one of the things that matters here is that the old ways of doing things, the old ways of thinking about object-oriented programming and HTTP request response are in many situations no longer good enough. And so what comes out of that is the idea of the reactive manifesto. And the way I summarize this is sort of we need to evolve with our users' expectations. And so the reactive manifesto defines something, the definition of what they call a reactive application. So a reactive application has a few foundational, I guess, truths about it. Reactive systems, as opposed to maybe some of the traditional request response systems, reactive systems are responsive under various kinds of workloads. That meaning they're going to complete your request in a decent amount of time, regardless of the amount of strain the system is under. Reactive systems are resilient, meaning that they are going to recover from unexpected behaviors. They're going to recover in the face of various infrastructure issues. They're going to recover in the face of code issues or exceptions or things that go wrong. Reactive systems are elastic, meaning that they can expand up and down. They can expand and contract as necessary in terms of infrastructure or components to be able to meet the needs of its users. And a reactive application is sort of inherently message driven. Now, what we mean by that is the idea of passing messages back and forth from component to component. We'll talk a little bit about how these factor into Akka.NET specifically and how they factor into the actor model in a little bit. But as a result of adopting these properties, reactive applications are flexible, right? Meaning they are able to be modified easily, they're able to be adapted more easily. They are sort of by nature loosely coupled, as they are defined as individual instances or sort of boundaries that are sending messages back and forth. Reactive applications are scalable, right? They're going to be able to scale up and scale out as needed to meet user demands. So they're going to be easier to change, goes along with flexible. I should probably collapse those bullet points. They're going to be fault tolerant. They're going to be able to respond in the face of change. And a nice byproduct of this is that reactive applications tend to be very fast. So let's talk about an overview of the actor model itself. Like, what do we mean when we say actors? What do we mean when we talk about the actor model? So the concept of actors is actually, while relatively new to .NET, is not really a new concept. This is where, if we were in the audience, I'd do some participation of when we think the actor model first came into being in terms of application development. And the punchline there, the end result, is that really the actor model sort of came into being with Carl Hewitt's white paper, which came into the world in 1973. So the actor model, or the idea of building systems based on the actor model or these components, is not a new thing at all. Now, we have just kind of come into our own in the .NET ecosystem in terms of the actor model and various frameworks and libraries that help us implement and achieve the actor model. But the concept itself has been around for quite some time. So I want you to know by this that you're not buying into some new fad. You're not buying into the next passing phase of things. This is a proven technology. It's been around for a while on various formats that we'll talk about in a little bit. So in fact, we'll talk about it right now. So where are the actors? Where do you find the actor model? So first of all, programming languages like something like Erlang or Scala, a lot of those have actor concepts, or we could say are loosely based on the actor model, and implement certainly the fault tolerance patterns that you see in the actor model. I believe the error handling methodology in the actor model really goes hand in hand with that, with Erlang. And so you'll also find them at any really companies doing things at scale like Box or LinkedIn, which I think uses, or at least used, Java Akka. folks have probably heard about Microsoft Orleans, which is a distributed actor model system, and that is another take on the actor model that's driving things like Halo on the Xbox and other sort of large immersive experiences. Also applications such as WhatsApp and using the actor model at scale to be responsive and resilient. But you're also going to find them in really bedrock systems. So think telecom systems, finance systems, systems that are doing really important data crunching. Systems, in other words, that really can't go down or you're actually going to have a lot of trouble on your hands. And so systems that have event streams or neural networks, a lot of these kinds of applications are where you're going to find the actor model and its concepts. Now, a lot of that probably sounds like where we want to go. We want to be able to handle massive multiplayer experiences at scale if we need to. We want to be able to respond and have our applications, keep that uptime that we know our users are depending upon. We want to make sure that we can get things done quickly. So where does Akka and Akka.net fit into this? I'm going to kind of butcher a brief history of Akka and Akka.net. So the way I understand it, and this is where it'll be fun if Roger or Aaron decide to come on here and correct me at some point, but the way I understand it is Roger and Aaron were working on this concept sort of separately. Aaron had a company called Marked Up Analytics, and he was doing going back and forth, doing their goal was to, if a user on an online store, for example, took 3 different actions in sequence or together, you maybe want to offer them a coupon or you want to offer them some kind of deal. And so Marked Up Analytics was a company that helped you sort of capture those events and do that. And they had written it using SQL Server as a database and doing HTTP requests back and forth. And I think the way he described it was that quickly fell over and caught fire. They couldn't really keep up with what they were doing. And he spent a long time Googling for the problem that he had, the problem that his company had. And he realized that he had a reactive, stateful fault tolerance problem. And so after being able to Google those terms finally, he stumbled upon Java's Akka library. And so at that point, the way I remember him telling it is that he said, okay, well, I either have to port my entire company's code base to Java, or I've got to port the concept of this actor model and Akka into the .NET world. And so he chose the latter. And the Akka folks, and at this point he also found Roger, I believe, because they were sort of working on this project separately, or working on these ideas separately, and so they teamed up to create Akka.net. And the name comes from generously the Java folks allowed them to use the name Akka, and so, or the folks who are in charge of the Java Akka project, and thus we have Akka.net. So that's the history in a nutshell of how that came to be. So enough of the history there out of the way. Let's talk a little bit about actor model concepts. What do we mean when we say actor model? So as you might have intuited at this point, in the actor model, an actor is a foundational concept. So we can think of, and similar to object-oriented programming, how everything in object-oriented programming is an object, the basic unit of work in an actor system is an actor. So you can think of an actor as an object on steroids. And every thing that you use within the actor model is going to inherit from some type of actor, which we'll see demos of that later, where you're going to inherit from receive actor or from untyped actor. So every piece of component that you have in an actor model system is going to be of some type of actor. And so what does that do? Well, being an actor out of the box, it's sort of an actor gives you a container for a bunch of different things. It's a sort of a container for the state of your object. It's a container for certain types of behavior that you want the actor to perform. It's a container that has a mailbox where an actor can receive messages. It is a container where an actor can have child actors or other actors in a hierarchy that it uses to help it process its messages. And it has a container for supervision. So what we mean is that when we think about an actor, it has all of those things bundled in one concept. And we'll show how those are used together a little bit later when we get to the demos. So as I mentioned, we are sort of encapsulating these various concepts, these different states, these different behaviors. So the other piece here is that actors are encapsulated based on an address. So every actor has an address within a system. So we talk to actors by reference. We get a reference to an actor, we send it messages, and then maybe it sends us a message back, maybe it sends messages to other actors, but we talk to those actors by reference. We're not really digging into the internals of an actor. It's encapsulating all of that in sort of a little black box for us. We're sending an actor a message, and that's how we're communicating with it. So it functions as one unit. I mentioned the concept of immutable messages. For those of you who are unfamiliar or are less familiar with the concept of immutability, we've got actors in our system sending messages back and forth to various other actors. Now, those are all going to be objects that we create. So like any object, right, we can create it however we want. So we could make that object contain state that could change. This would be very bad for our actor system. The actor system is predicated on a message being the same when it leaves an actor as when it arrives at the recipient. And so when we build messages, we make sure that those are immutable, meaning their contents cannot change. And so we'll show some examples of that for those of you who are less familiar. But think of it like, okay, passing in, right, having private setters and public getters for the properties of a message, and taking in all of those required properties as part of the constructor, things along those lines. But the key there is that the contents of a message cannot change, and we need to build our messages to make sure that that's the case. So we're not going to use a list necessarily. If a message contains a list, we'll use an immutable list, for example, so that nobody can change the contents of it. I mentioned actors by reference, and this is going to be a really important concept in the actor model. So when we think about an actor, when we have a reference to an object, right, we may say var x equals new something or other, some new kind of object there. However, in the actor model, we're not getting references to actors directly or creating new actors that way. We are getting references to an actor based on its address within an actor system. We'll talk about what the address is, where that fits into an actor system in a little bit. The reason that we care about actors by reference, though, is that enables some of the key benefits of the actor model, as we'll show as one of the demos here tonight. Another important concept in the actor model is the idea of props. And so the props are what we use to create an actor. And so it's sort of, think of it like a recipe for initializing an actor that's going to do some work. So if you build an actor, props are going to be the things that actor needs in order to instantiate itself and to run. So initially I thought when we were dealing with props, like, oh, that's properties of an actor or something like that. No, it's props. Like if you're a stage actor, you need props to do your job. So we pass props to an actor in order to set it up for success. As I mentioned, actors have, every actor has a few concepts in common. Every actor is going to have an address within an actor system. So it's going to live within this system. It will have an address, which is a place where we can get a hold of that actor for the entire length of time that it's alive. Every actor has a context. So every actor, as I mentioned, lives in an actor system. That means that you're either going to have a top-level actor or actors underneath of that actor, child actors as they're often called, and that's going to form a sort of hierarchy. But actors don't sort of exist on their own where we're just newing up an actor. We're going to always sort of say system.actor of. And so we're going to put an actor into a system, or we're going to say that an actor is a child of another actor. Now, this is key because forming that hierarchy is one of the things that allows us to enable the fault tolerance that we're looking for in applications. So every actor lives within an actor system. There's always that idea of a context of where that actor is operating. Every actor has the idea of supervision, which is to say that actors supervise their child actors. If something goes wrong with a child actor or an actor lower in the hierarchy, the parent actor has some responsibility for supervision of that child actor. And so we'll talk a bit about how that enables fault tolerance in a little bit as well. And every actor has a mailbox. Remember, I mentioned that actors are sending and receiving messages. So as part of inheriting from a receive actor or an untyped actor, you also have access to a mailbox. Now, every message that comes into an actor is processed in the order in which it was received. So it's sort of a first in, first out queue. And so you can, Akka makes the guarantee, or Akka.net makes the guarantee that your mailbox will fill up and your actor will process one message at a time from that mailbox. And so every actor has that mailbox where it can receive messages. And lastly, amongst other things, every actor has a life cycle. This is to say that every actor has life cycle events when it restarts or when it stops, and you can hook into those life cycle events in order to build resilient systems or send other messages or take other actions whenever an actor is shutting down or restarting. And we'll show a demo of that as well tonight. So an address for an actor. The first part of the address of where an actor lives is the protocol. So in this case, we have an actor and the protocol of which is akka.tcp. So we're using the TCP protocol in this instance to locate that actor. Akka.net, I believe, supports TCP out of the box. I think it's configurable with others, and I think you can even write your own if that's your jam. But I typically go with the standard, out of the box TCP for my systems. I haven't had a reason to go beyond that yet. So the first part of that address there is the protocol. Next up, we have the name of the actor system. So this is important because you're going to need to share that name, that actor system name, if your actors are going to communicate with each other, say in a cluster, or say if you've got remote machines that are talking to each other. That actor system name is important. And so the actor system comes first in that actor's address. Next, you have the address of the machine that the actor is located on. Now, in this case, the actor is shown as running localhost 8080. If it's a remote actor, maybe you're going to have a remote IP or something along those lines. And so the localhost there is going to be the address in this case. And it has a port as well. In this case, the port is 8080. And then lastly, we have the path. Now, this is important. So we see that first slash there in the path, there's actually a hierarchy of actors, as I've mentioned before. Now, Akka has a slash, which is the top of the hierarchy, and then it has sort of two sub-hierarchies underneath that. There's the system hierarchy, and then there's the user hierarchy. Any actors that you create are going to live in the user hierarchy. So anytime you see an actor that you create, that slash user is going to be a part of that address. And so in this case, slash user slash hello world actor means that we have created a top level actor, and the name of that actor is hello world actor. And so that's to just make sure that folks understand that user is an implied concept there. Akka.net has its own system level hierarchy. Anything that we do is going to be under that user hierarchy.
Sean, there are a couple of questions.
Great. Let's. I'm not able to have them up on my screen, but I'm happy to hear.
Yeah. So the first one is Akka versus Dapper ? Thomas, if you want to further explain that question, come off mute. Or if you're not able to. So I guess the question is, this Dapper that's used with Kubernetes and other things for side loading. So I guess Thomas's question is, what is the difference between that versus Akka?
Sure. So I have to be, this is where I have to, my lack of familiarity with Dapper is going to come into play. So my understanding, which I have to say, take with a grain of salt, and I'll confirm after this, is I believe that Dapper is making a play in a slightly different space. I think that, Dapper, and I'm literally Googling it right here to make sure I'm getting this right, because I have no problem looking up things as we go. So Dapper is sort of trying to abstract away, it appears, the differences in different applications. And so it does have some of those actor model concepts. I don't know that it's intending to be a replacement for Akka.net or a competitor to Akka.net. It looks like what Dapper is really trying to do is simplify the nature of distributed applications at a slightly larger level. I see Akka.net as a reimagining of how we think about object-oriented programming overall versus how we might think about interactions between microservices. However, again, take that with a grain of salt, and I'm going to look into that a little bit further after this talk and make sure that my answer just then wasn't completely incoherent.
Okay,
so with that, we'll hit the next question.
So the next question is actually it's from me. I'm not familiar with the protocol you put in akka.tcp : // Is it similar to like HTTP or even like some of the queuing protocols like AQMP and other things like that? And is it widely recognized by
Sure,
applying some tools?
That's a great question. And so the way that address is structured there, in fact, let me go back to that here on my slide. So the way that address is structured there is that Akka is saying the protocol in this case is that you are using Akka's protocol handler, is I believe what that means. And then you are using TCP as the protocol for Akka to send messages back and forth to other actors across the network. So if you were talking from machine to machine, you will be using the TCP protocol to send those messages. I don't think it intends to have Akka.tcp be its own protocol. I think Akka is saying that you're using the Akka TCP handler to send messages, TCP being the network level protocol there.
Yep, and Thomas just posted you answered his question, and you answered
Okay.
my question too. Thank you.
Oh, 2 for 2 so far? I will take it. All right. So every actor also has a life cycle. And thank you, by the way, for stopping for questions. That's definitely feel free to keep doing that. So every actor has a life cycle, as I mentioned. So let's look at the act of restarting an actor. So I'm going to see if my fancy, there we go, my fancy pointer is going to work here. So when an actor is going to restart, when an actor is going to restart, the first thing that happens is a pre-restart event is called on the old instance. Now let's let you do some things like, hey, maybe make sure all of the messages that are in your queue aren't going to disappear, or tell somebody else that you're about to restart or shut down, or whatever the lifecycle event might be there. And then what happens is the restart is called, the new instance is created, the new instance replaces the old, post restart is called on the new instance, in which case you can say, hey, I'm back up again, or I'm ready to process messages, or notify whoever you need to notify that things are back up. And then resume is called on the new actor instance, and it resumes processing messages. And we'll have an example of how we can use these lifecycle events to our example, or to our advantage, to make things a little more fault tolerant. But mostly I wanted you to know that these ideas of pre-restart, post-restart, resume, these are built into every actor, and these are the kind of things that you can hook into to help make sure that the rest of your actors or the rest of your system is aware of what's going on and is resilient. So I mentioned context, and context.actorOf is what we use to create child actors at the top level. So if we want to create that hello world actor, we would call context.actorOf, and we'd pass in the props to create our actor. And so that's going to help that actor live in that top level context. So every actor has that context, just to reiterate that. And so here's one of Roger's great graphics that I absolutely love here. So what we have on the right-hand side there is an actor ref. So we have a reference to an actor. It lives somewhere. We don't actually have to know too much about where it lives. Akka handles a lot of that for us behind the scenes. It passes through some sort of transport like the TCP protocol that I mentioned, and messages are going to come into the actor's mailbox. Couple key concepts here. You see that the actor processes one message at a time. That's a key concept and a guarantee that Akka seeks to make. You are going to have messages processed in the order in which they are delivered. You're not going to have to worry about processing 3 messages at a time. Messages queue up in a mailbox and they're processed one at a time by the actor. This also happens on an event-driven thread. What we mean by that is that there's no polling. Your actors aren't sitting around like a queue consumer maybe saying, hey, is there any more work for me to do? Is there any more work for me to do? An actor uses relatively little CPU while it's sitting there waiting to do anything. In fact, it uses virtually none. So when an actor processes a message, it can do a few things. Maybe it's going to perform some behavior. It's going to tell another actor another message, or do some computation, or kick off some work to some of its child actors. Or maybe it's going to alter its behavior for the next message that comes in. Actors are capable of doing that as well. Maybe it's going to modify some of its internal state, or capture some of that internal state there. Or maybe something's going to happen with supervision. Something went wrong. It needs to blow up or throw an error, or raise some kind of supervisory concern from where it is. And so one message at a time from the mailbox. The transport is transport agnostic, right? We can use whatever protocol as long as the rest of the actor system understands it. We can send messages however we want, and we have those kind of behaviors and state modifications that are done as part of receiving a message. Next up, we've got the idea of that fault tolerance that I was mentioning. So when we think about faults, let's think about maybe a traditional, I'll call it old school at this point, or standard, classic maybe, line of business application in a classic OOP system. So let's think about what might happen here. So say we have a service, right? And say we have a, some kind of service. It's got a business logic layer, maybe, if we're doing some kind of layered development like we have done many a time. Then maybe we have a data access object that business logic layer is working with. Maybe from there we've got entities or entity framework or something like that, and an entity. So what happens when something goes wrong at that lower level, right? At that point, you're sort of in the world of exception handling, right? And I don't know about you, my exception handling personally, not perfect. And so one of the things we want to think about is those exceptions may or may not bubble up. They may or may not cause problems for the user. They may or may not grind the entire system to a halt, depending on how we've caught those exceptions and whether we're handling them well. It's also unclear in that situation who's responsible for handling errors. Is it the caller of the object that should be responsible for handling every error? Is that really is that really a wise strategy when we think about all the different ways these various objects could be called? Is there a system that will allow us to reason about that a little bit better and think about those handlings and that fault tolerance? So this is where we get to that error kernel pattern, which I mentioned is pretty prevalent in Erlang, though to be clear, I'm unfamiliar with Erlang itself, and I probably should brush up. But I understand that it's a pretty prevalent pattern in that language. And as I mentioned here, we have those two hierarchies of the system hierarchy and the user hierarchy. The parent actor is responsible for any child actors that it creates. So the nice thing about this, when you're thinking about it, when you're building out your actors, is that we're actually sort of thinking about this at development time for each actor. Okay, hey, what happens when something goes wrong with this actor? Okay, as a parent actor, I'm going to do this when this kind of behavior happens with a child actor and an exception is thrown. So we have already put in a little more thought than we might normally about exception handling and the ways to do that well. And so the parent is responsible for its child actor, and we're doing a lot of that thinking up front. There's some built-in strategies in Akka.NET for how to think about failures and how to think about fault tolerance. So the two examples are here. So if we have our root level hierarchy here, and then we have our user hierarchy on the left-hand side, and we have our, maybe an object that's or an actor that's at message A or address A1, and then maybe a child actor of that actor that's at address B1, and we've got some C1 and C2 actors under here. If actor C1 here on the left blows up, actor B may have specified at development time that it's going to have the one-for-one supervisor pattern. Now, what we mean by the one-for-one supervisor pattern is that whenever a child actor does something wrong or blows up, we could take a certain action on only that child actor. We could restart it, we could stop it and have it refuse to process messages. We could, replace it with a new actor. We could take some other rerouting of messages away from that system. We can do a number of different things. But in this case, we mean that we're going to take action on that specific child actor. Here on the right-hand side, we have the all-for-one supervisor pattern, which is to say, if actor C3 here is to experience a fault or some kind of exception, maybe we're going to take an action on all of the child actors there to make sure that they're being reset into a reasonable state, into a state that we can reason about. And so those are just two of the out-of-the-box supervisor patterns that are available in Akka.NET. There are a few others, and as well as, of course, you can create your own and implement that however you'd like, and there are documentations on how to do that. So the key there is that you have great out-of-the-box support for doing various kinds of common tasks. You also can build your own sort of supervisory structure without I would say without a huge headache, if that's something that you're interested in or if you've got a specific need. So why would we go to all this trouble? Why would we restructure our applications? Why would we make everything into an actor and try to think about these supervisory patterns? What does that get us? One of the things I love about the actor model in Akka.NET that I didn't really think I would at first is the idea that everything, actor systems are sort of async by default, or rather, I don't have to think about the asyncness of an actor. From an actor model perspective, my actor is processing a single message. So I write my code to deal with the effect of processing that one message. I don't have to worry about something trying to process 14 things in parallel, and do I create a concurrent bag to put things in instead of a list? With an actor, I can have that internal state. I only have to worry about one operation at a time and processing the result of that operation. So I can have a list in my actor's internal state. I don't need to have a concurrent bag, because Akka is what's helping me make that guarantee that I'm going to be receiving one message at a time from my actor. So what this has done for me, well, one, my async code certainly isn't perfect, and I'm willing to bet that some of your async code is not perfect either. One of the things it does is it makes it a lot easier for me to reason about async code, in that I can kind of offload a lot of that cognitive overhead to the actor model framework. And I can think about processing a message, what it means to process a message, how I want to think about delivering that message, or where I want to send that message in my system. What Akka.NET is allowing us to do, therefore, is it's dealing with the event-driven thread. It's dealing with the pool of various actors. It's dealing with the transport level issues, and making sure that those actors are receiving those messages, and making sure that those things are handled asynchronously as possible. And so I think that in this case, I really enjoy the ability to reason about the asynchronicity of my application without having to have that front and center and be coding for it all the time. In applications where I'm really trying to make that responsive, I have found it to be a big productivity boost, and much easier to debug and think about what's happening than when I'm trying to debug my async code. I mentioned recoverability. We won't go into that. Won't beat that too much. Beat that drum too much in this slide. But remember that the key there is, if something goes wrong at every point in that hierarchy, you have the chance to recover from it. And if every one of those objects has a supervisor, a supervisory strategy, every one of those actors has a supervisory strategy for its children, then we really have a lot of opportunities to recover in a way that doesn't affect the system overall. And so we get some of that resiliency and recoverability, and we'll demonstrate some of that recoverability in our demos this evening. So we also have the ability to scale work out across many actors. If you have dangerous work that you're doing, you push it further and further down in the hierarchy. You push it to those child actors. Maybe those child actors are breaking up work and pushing it down to children of their own. That dangerous work gets pushed down in the hierarchy, and you get many, many more opportunities to recover in the face of failure or unexpected behavior.
There's a question from
Sure.
Anthony. Anthony, do you want to ask a question?
Yeah. Can you hear me?
Yes, I can hear
Hello?
you.
Okay, good. So my question goes this way, okay? This is my first time of hearing about Akka.NET, and I found it interesting. But I want to ask, is this like a sub or a super version of RabbitMQ? So I have microservices, and I'm using RabbitMQ to send messages across microservices, okay? Would Akka.NET replace such process and do more advanced things for me?
That's a great question. That's a really good question. So the way that I think about the Akka model, and the way that I've heard other people think about it, is it's not necessarily it's a great foundation for your microservices. If you have a stateful sort of microservice application, Akka.NET may be a really good choice for building out a cluster for processing various pieces of information and ensuring that you have that recoverability. In terms of the message bus, we've often heard, like, how does Akka.NET work with message bus or with service fabric or something along those lines, so for RabbitMQ. And the way I think about it is, Akka.NET doesn't need to compete with a message bus, but typically in situations where you have RabbitMQ or something along those lines, Akka.NET is oftentimes a great choice for something to pull messages off of that service bus, take action on those messages or off that RabbitMQ queue, take action on those messages, and maybe put other messages back onto the queue. And so what you have there at that point is something that, if you already have a queue system in place, having something that can be scalable and recoverable at that level may make Akka.NET a wise choice. We don't talk about it in this talk, but a few other things that Akka.NET has going for it is the idea that Akka enables you to build and reason about clusters of machines and clusters of workers in a really nice way. Akka also has something called Akka.persistence, which allows you to store messages as they come into the back end of your choosing, such as SQL Server, or Cassandra, or other things along those lines. And so if you were to cut that message bus out of your system, you could have a cluster of actors that receive a message directly, and then persist that message to the backend store, and then the cluster processes it. So it could take the place of that, but my point is it doesn't need to take the place of that. They can work in harmony with each other, and it can Akka and the actor model and Akka.net can be a really good resource for pulling those messages off and processing them. Does that answer your question a little bit, at least?
Yeah, like to a large extent. But one thing is that I'm not gonna say that RabbitMQ does not really help or solve part of the problems I have when it comes to messaging. But one problem I do have is a way of storing messages that come into a database. So I have that challenge. So I don't know what comes in. I don't know what time it goes out. Like I don't have an audit of information that goes across microservices. That is one major problem I have with RabbitMQ. But from what you said, it looks like Akka.net would handle that very perfectly. So I would give it a try of seeing how it works.
Sure. So I would mention that, I think that depending on your specific application demands and really the purpose that those queues are serving, one thing that is something to keep in mind is that a RabbitMQ message isn't necessarily going to be the same thing as a message that's getting passed back and forth between actors. So you're still going to have that kind of idea of an incoming message to some sort of actor that ingests it, but that actor, if it's using Akka.net, is capable of doing that persistence. So it's just to mention that what you'll want to think about is what is the purpose of that queue, how is it serving that? Because while you're going to do Akka persistence potentially, if you're not architecting that system specifically around event sourcing or around applying those events to the actors, it's not like you're going to get automatically an audit log of everything that's been persisted, right? So there's still work that you're going to have to put in there to work around that and to build that into the system. But my point is that it certainly is capable as a cluster of receiving that. But if you're looking to get all of those business benefits that you just mentioned, Akka, in my understanding, can do that, but it's going to be a little bit of work. You're going to have to sort of build with that in mind, if that makes sense. And we'll look at that. And so what I will say too is that I think that part of that Akka bootcamp does talk about clustering and how it works there. And if not, Petabridge also has some great training courses that are, I think, last time I checked, were reasonably well priced. That if you're interested in sort of those concepts and seeing if it would work better, one of the courses is specifically around modeling systems for those kind of concerns. And so you may find some benefit in that. And I think it's like a full day course, and it was very reasonably priced last time I checked. So feel free to look into that as well on the Petabridge site. Sure. So moving on to the next benefit of our actor model there. So actors are cheap, which is not just a jab at actors. Sorry, I'm a theater kid, so I feel you're paying actors. But no, actors are not necessarily cheap as people, but the idea there is that actors and the space that they take up in your system is relatively cheap. The latest figures that I pulled, one, as I mentioned before, actors use no CPU unless a message is actually being processed, because Akka is providing that sort of event-driven thread for capturing things. And in terms of memory footprint, I believe you can, the latest figures I pulled were that you could do 2.5 million actors per gigabyte of RAM. So roughly speaking, that's a lot of actors, and it enables you to have some really great patterns, such as an actor per entity in your stateful actor system, or some really specific fan out scenarios where you may need a lot of parallel processing power. And so 2.5 million actors per gigabyte lets you create a lot of actors in your system and lets you think a little bit more broadly about how you might represent actors in an actor hierarchy. In terms of throughput, I also have a figure here, and I haven't tested this myself, of 50 million messages per second on a single machine. So of course, we're not talking network boundaries at that point, right? We're not talking around those lines. But in terms of the raw throughput and power of processing messages concurrently on a system, that takes you a long way if you're still scaling up. So the next benefit here is the idea of location transparency. As I mentioned, you don't have to know where an actor is operating. And this is great because if I send a message to an actor, I don't know if it's one actor. I don't know if it's on a remote system or if it's on my local system. I don't know if it is actually behind a router that goes to 5 different parallel actors. All I know is that I have a reference to an actor and I'm sending it messages. So this is akin to the cell phone, right? If I want to call my brother on his cell phone, as I often do, though he may wish that I don't. No, when I want to call him, I only have to know his cell phone number, right? I don't have to know the 14 cell phone grids that call hops through in order to be processed. I don't have to know how all of that infrastructure works. I have a reference to his phone. I dial that phone, and then that phone is picked up, right? Or I get voicemail, or he says, "Hey, text me." Phones are for old people. So sometimes, we'll get some of that. But no, I think that the idea there is that it's important that you don't have to know where an actor lives. You get a reference to an actor and you're able to send it messages. And that's a very powerful concept in the actor model. So same or different process, same or different machine, doesn't matter. You can send a message and Akka will tell you if that message can't be delivered. The idea in Akka.net and in the actor model in general of enabling easier state machines. I mean, easy is always a relative term, right? So I hesitate to say easy for anything. But actors have the concept of become and unbecome, where an actor can change its behavior for the next message based on whatever the current message says. We'll demonstrate this in a little while in our demo code this evening. And so it can actually change how it will process the next message. And this enables the idea of state machines or making those a little bit easier to reason about as well, because you understand what the behavior is going to be based on the message that comes in. And so being able to change an actor's behavior on the fly like that is another really powerful concept. Akka.net uses something called HOCON, or Human Optimized Config Object Notation. I know that you all love another configuration language to use, but no, it really is not too shabby as far as configuration languages go. Has configuration fallback, has the ability to do layered configurations, and as you'll see this evening, it's not so hard to read. But one of the big benefits of configuration is that you can actually change how actors are deployed. So let me help visualize how that might come into play or how we might find that to be beneficial. So, in the olden days of software, or really not too long ago, honestly, we had our code, and our code was single core. And so it didn't matter if we had an 8-core processor, our code was only living in 1 core, right? This is before the days of async, before the days of the way we're dealing with multi-core processors. And so no matter what code we wrote, it was always going to live in that 1 core. So our code was single core. Then we came along with multi-threading, right? So now we can do multi-core, right? We've got a 4-core processor. We can actually make use of that. So you can use TPL or async await to take better advantage of those scaling and getting more out of our processors. So we can actually make use of those cores. So that's great, and that takes you, up and up and up until you've got however many core processors the latest whiz-bang CPUs are doing these days. But your code can take advantage of that up to a point. But what happens when that's not enough? What happens when you hit that scale up, wall for your application? Right? Well, that's a lot of us are hearing, or a lot of us have hit this at different points. And once you get to a spot where one machine isn't enough, now you've introduced a whole slew of other concerns, right? It's not just now you adding more code is adding more machines becomes problematic. You have to introduce a RabbitMQ type service. You have to introduce other infrastructure to make sure that those different machines can process things together. Also, you have to make sure that those things are coordinating their deployment. So you get things like queues or service buses or things along those lines to help kind of introduce intermediaries between that. However, one of the key concepts of Akka.net is that scaling up and scaling out are the same thing. With actor configuration, I can actually say, hey, this actor at this address should actually live on this remote machine. Or this actor at this address should actually be 25 actors behind a router. And that can all be done through configuration. And one of the nice things about that is that I don't have to modify my code in order to make that happen. So scaling up and scaling out are drastically, the cost of scaling out, I should say in particular, is drastically reduced if you're building this using the actor model, using Akka.net, using some of that elasticity up front. When it comes time to move beyond that machine barrier, rather than having to re-architect some core pieces of your application or introduce that additional infrastructure, you can move into a cluster of actor machines that already know how to talk to each other, that already know how to pass messages back and forth, and you can have Akka, the framework, enable you to handle that, and it all happens transparently, which sounds pretty good to be true, and I hope to demo that tonight in some ways. And in fact, I think we're hit about time for demos right now. And so what we'll do is I'm going to go ahead, and I'm going to share my other screen. I'm going to go ahead and drag Visual Studio over here. While I'm doing that, I just want to show you a sort of no tricks up my sleeve thing here. Prior to this demo or this talk tonight, I have run a Terraform script. I left my console log here open just so you can see that I just did it. Just did it at 8:16 here. Sorry, that was from before. So I guess you have to trust me that I just did it tonight. But I deployed an Ubuntu VM into Azure. It's just a plain Ubuntu VM. I have done nothing to it other than I have, I'll just again, no tricks up my sleeve. I'll go to the top of my console here. I have installed, I've pulled this presentation repository from Git. I have installed, I've run this install stuff.sh. What that does is it's installing .NET Core and or .NET 5 and a few other things like that. But that's just the basics. We haven't actually built or run my application at all yet. So that, I just want to be clear. We have some empty code here on an Ubuntu VM that is running in the cloud. So no, nothing up my sleeve here for this. I just want you to be aware of that. We'll use it in a later demo. As I go ahead and bring up the next the demo application here, definitely happy to continue to take questions. Go ahead and put that on the screen here. Okay. Let's start this evening with an understanding of Hello World. What does Hello World look like in the actor model? And definitely let me know if this text is too small or is difficult to read. So what we'll do is we'll walk through. Oh, sorry, great question. I did see it pop up now. Excellent. Now that I'm in Visual Studio, I will be posting the GitHub repository over there. It's also that presentations repository is where it is. So on the intro slide here and on the end slide tonight, that address, seanklee.com/presentations, that's going to be the GitHub repository. But I'll definitely post that as well at the end of the night. All right, so let's look at Hello World in the actor model. So here, and I apologize, I'm sort of looking away from the camera. I just got it up on my other monitor over here, so I'm not ignoring you. Our program here, we've got all of these demos are going to be console applications, and we'll walk you through line by line what they do, and then we'll go ahead and run them. So the actor system, the first line here in our console application here is we create our actor system. Now you're only going to create one actor system. You may create many actors, but typically you're going to create one actor system. Actor systems are much more expensive to create than actors. We typically are only going to have one per application. So in this case, my actor system is named Hello World System. I then create a new Hello World actor, and I get a reference to that. I create it via system.actorof. Remember, that's going to put this actor right under that user hierarchy in our system. And it's going to, we're going to create it using props.create, which is sort of the equivalent of an empty constructor. Props.create hello world actor. It doesn't need to be passed anything to instantiate itself. And we're going to give it a name of hello world actor. And then so that actor is going to live at /user/hello world actor. And then we have a sort of an infinite loop here. And while we're in that loop, we're going to enter your name, and we are going to get that name. If the text that we type in is equal to end, we're going to tell the hello world actor a new finished message. And if we enter anything else, we'll tell the hello world actor a new hello world message. So let's go ahead and look at the contents of these messages here, and then we'll look at what the actor itself does. So for example, the hello world message, you'll note that when we create a hello world message, we need to pass in the name that was entered. So if we look at our hello world message here, we see that it's setting this property in the constructor, and then it only has a public getter. So it really has one property that we can access, and that has the name that was passed in. The finished message here is actually just an empty object, right? We're telling it a finished message, but there's no actual contents that we need. The contents are in the name of the object itself. And so the hello world actor, look at what that does. The hello world actor here inherits from the type of receive actor. Now this is what's provided by the framework. So that actor, the hello world actor, has an iActorRef or an actor reference to something called a console writer. So here in our constructor for the hello world actor, we see context.actor of console writer actor. So this is going to create an actor that's a child actor of the hello world actor. It's going to put that reference into this variable here so that we can then send messages to that console writer actor. In the constructor of our hello world actor, we also have this receive method that is provided by the framework. When we receive a hello world message, we then have a handler here, a handler lambda. And what we can do here is we can tell, in this case, when we receive a hello world message, we're telling the console writer a new write something message. And the contents of that write something message is a string in this case, hello, comma, message.name. And so if we receive a finished message, the console writer, we're going to tell the console writer a new write something message that says, I guess we're done here. And let's look at that console writer actor. It too inherits from receive actor. It doesn't have any other actors that it uses. And when it receives a write something message, you'll see it's going to show console.writeLine. And it's going to, in brackets, show the sender's path, and then whatever that thing to write was as the message. So let's see that in action here. Let's go ahead and run our hello world application. All right, so we should see here, enter your name, right? So we'll go ahead and say Santosh, so we go hello world system /user /hello world actor. Right? And so we see again, enter your name, Bob, but notice a couple things happening here. I entered Santosh's name here, and we have the enter your name came next, but then we saw this console output asynchronously. Right, so our console loop is running there, our infinite loop is running, but things aren't necessarily being processed, right? Things are being processed or sent to the console asynchronously still. And so enter your name, right? We do Sean, Bob, Ryan, right? And we can see here that what's happening is a hello world actor is receiving that new hello world message. It's then telling the console writer actor to write out that write something message, and we're seeing that appear in the console as the result of the work of that console writer actor. So that is the hello world of the actor system as far as I'm concerned. We have an actor that uses another actor to do something, and in this case, it's to send something to the console. So those are some of the basics of creating an actor system, creating an actor within the context of that system, sending that actor a message, and having it perform some kind of work. Okay. So what to look at next? Let's look at becoming and unbecoming. So we have here an actor that is going to change its behavior. So again, we have a demo where we are creating an actor system in our console application here. We're calling the actor system become unbecome demo. We have a variable called variable writer, which is going to use this variable console writer actor. So we're creating a top level actor of this variable console writer actor. We'll look at what that does in a second. In console.writeLine, we have say some things, and then we have another infinite loop, and it's going to read the text that we enter, and it's going to tell the variable writer a new write something message of text. So we're reusing that write something message. So let's look at what this variable console writer actor is going to do. We see here it's going to inherit from receive actor, like our other actors have done. And we also see this I with unbounded stash. So we'll look into what that does as well. What we see here is that in the constructor of the actor, rather than the receive method itself, we have become normal writer. Normal writer here is where we can now put our receive methods. So whenever things are normal and we see receive a write something message, if the message that we write is be quiet, it's going to say zipping my lips, and then it's going to become a quiet writer. Otherwise, if the message isn't be quiet, it's going to write out that message to the console directly. And then we also have down here quiet writer. So we have become quiet writer, which means we can pop down here. And now when it's in that quiet writer state, if it receives a write something message, unless we say be loud, it's going to stash that message. And that's where that I with unbounded stash comes into play. It enables us to call this stash here. And so otherwise, if we say be loud, it's going to say letting it all out. It's going to unstash all the messages that it previously had received, and then it's going to become a normal writer, meaning those messages are going to go back into the mailbox of the actor. It's going to become a normal writer, and then it's going to play those messages back and process them as a normal writer, or that normal writer state that we created here. So let's look at how that works in effect. All right, go ahead and run that demo. Bring that over. So we say some things. We'll say, hello world, how are you? We've said some things. Okay, now we'll say be quiet. We see zipping my lips, and then we can say, okay, hello world, Akka.net is great. Right, so we're not seeing that output, right? Those messages are now being stashed by the actor as it comes in. Now we're going to say be loud. And then we see those messages are processed again in the order in which they were stashed. So we can see hello world Akka.net is great coming through from our stash into the actor's mailbox and being processed in that normal way. So this is an example of some of those features that you get out of the box with Akka.net in terms of being able to stash those messages and change behaviors. All right, now let's talk a little bit about supervision. So we have here, again, another console application. And here we're calling our actor system the supervision system. We have a parent actor, which again is going to be a top level actor there under that user hierarchy. We're passing in again some empty props essentially. And we are giving it the name parent actor. So this actor is going to live at /user/parent actor. And now we see here that we're not creating we're not passing it around as a variable. We're actually just going to create a reference. It's just out there at a location. So we're also going to create a high-level actor, or a top-level actor rather, called, we'll use that console writer again in this case. So we have our /user/parent actor, and we have /user/console writer. Then what we're doing is for every item from 1 to 100, we're going to tell our parent actor a new process a number message that takes in that number. And all it does is capture that number as a property. So we're going to tell our parent actor 100 times a new process a number with that number. So what does this parent actor do? Again, inherits from receive actor. We can see here there's a reference to something called volatile children. So what we have here, and actually this should probably be volatile child in the case of this demo. It used to have multiple, but we simplified it. So in the constructor for this parent actor, our props are we create a volatile child actor. And so we have a child actor called children, but it happens to just be one actor in this case. So in fact, I'm just going to go ahead and, well, we'll leave it for now. We'll go ahead and say creates a child actor there. And then when the parent actor receives a process a number message, it simply passes that on to its child actor. It tells it that message. We also have here a supervisor strategy, which will talk a little bit about how those things are going to work in a minute. So let's look first. Okay, so that parent actor just passes that on to the volatile child actor. What does the volatile child actor do in this case? Well, we can see here, we also have a stash, or the idea of a stash here. We inherit from receive actor. We've got a reference to that console writer. And we have an int here that we're going to increment. We're around processed numbers. So note again, rather than passing in that console writer through dependency injection or something like that, we're giving it a reference based on that path. Remember, I said it was going to be a /user/console writer. Well, here's that path being mentioned directly. So now we can, rather than having a child console writer for every single actor in our system, we can have one top level one and reference that if we want to. When this child actor processes a number or receives that process a number message, what we're having happen here is if the number of processed numbers is 6, it's going to reset it to 0 and it's going to throw an exception. I already processed 6 numbers. I'm too tired to process number, and then whatever the number message is that is processing. So if otherwise, it's going to tell the console writer write something message that says it's processing a number, then it's going to increment the number of messages that is processed. So as you can imagine, this is going to fail for every a 6th message that is received here. So let's see what this looks like in actuality here as we actually run the demo. So go ahead and run that supervision. Now we see here an exception is thrown. I already processed 6 numbers. I'm too tired to process number 7. We can see here, though, something happened. If we look at our console application, we can see that it processed numbers 1, 2, 3, 4, 5, 6 through the exception on number 7, and then things stopped. So what happened here is we can see here that some of these messages are sent to dead letters because that actor is being stopped when an error occurs. Now, this is part of the supervision strategy. So let's go back to that parent actor and look at that supervisor strategy. We can see here we have a 1-for-1 strategy. So when a child actor fails, we say we're going to stop that actor. Stopping an actor prevents it from receiving any messages that may come to that actor's location. There's no longer an actor there to receive those messages, so they go into what's called Akka's dead letters queue or dead letters collection there. So rather than directive.stop, let's look at directive.resume. So rather than do anything or restart or any of that stuff, we're just going to keep barreling through when we get an exception, when an exception bubbles up. So let's look at what that looks like in reality here. So now we hit our supervisory application here. We have it starts up. And we see, again, I already processed 6 numbers, too tired to process number 7. I'm going to go ahead and, I already processed 6 numbers, too tired to process 14, too tired to process 21. I'll go ahead and just click that a couple more times. Now look at what we've got here. Okay. Well, we can see here, 1, 2, 3, 4, 5, 6. The application continues, but we're missing message number 7 here. We're missing message number, 14. We're missing message number 21, right? So our system has kind of lost some processing there. It's lost some of those messages that we wanted to process. So that's not too great. So what would happen here if we went ahead and restarted the actor instead? Go ahead and look at how that would affect things. So let's go ahead and restart that actor when it causes a problem. Now we see our process 6 numbers, too tired to process number 7, right? Same thing, 14, 21. Let's look at what our console looks like here. Again, we're still missing that 7, right? We're still missing 14 because we've just restarted the actor, right? We have, we've reset the state, we've restarted the actor, but what we haven't, and then we've called resume, so we're processing messages, but we still didn't capture the fact that, what do we do with that message that we lost, right? What happened to that exception? So here's where we can start to look at our restart, our understanding of what to do with those lifecycle events. If we go to our child actor, our volatile child actor here, I've got some stuff commented out. We can see here that we've got that pre-restart method and that post-restart method. We used that stash concept earlier to stash some messages. So here's what we're going to do in this case. We have, when pre-restart is called, we're going to stash the current message and all of the other messages that we have. And then, which in this case is really just the one message. We're going to stash all of those. And then after the actor is restarted, we're going to unstash all of those messages. So note that this includes when an exception happens. When we call the actor to restart, it's going to understand. We can have access to the exception here. Maybe we only want to do things if it's a certain kind of exception, et cetera, et cetera. We can have those options here. We're going to stash those messages, and then when we restart, we'll deal with them. So let's see how that works out now that we've got the restart directive here, and we've got some processing there for the child actor in those lifecycle hooks. Okay, so things still fail. I already processed 6 numbers, too tired to process number 7. I already processed 6 numbers, too tired to process 13. Previously it was 14. 19 instead of 21. What's happening here? Let's hit continue a few more times and see what's going on. If I look at my console application here, I actually see that it processed 1, 2, 3, 4, 5, 6, and 7. Right? We stashed that when an exception happened. We were able to retry it. And because we'd stashed all those messages in the mailbox and then unstashed them when it was time to process, we actually still get them all in the appropriate order. So we see 1, 2, 3, 4, 5, 6, 7 is there, 13 is there, 14 is there, 20 and 21 are there. And so we have all of the messages that we would expect in the order in which we would expect them. And I didn't really have to modify too much of my code to enable this scenario to happen. And the nice thing is, because every actor can have a supervisory strategy, I already can be prompted to think about this up front when I'm building my parent actor. Okay, it's a parent actor. What is its supervisory strategy for child actors? And then when I'm thinking of my child actors, how do I want them to deal with exceptions or deal with their own children's exceptions? And so we have that sort of built in to that strategy there. By the way, I have this as stop at first, just for purposes of the demo. I believe the default supervisory strategy is restart in this case. Okay, so that's the demo of supervision. And now next, I want to talk a little bit about routing and how we deal with routing, how we think about some of the scalability of the actor systems here. So we're going to go into a slightly more complex demo. Let me close some of these other windows here. All right. So what we have here in our oops, sorry, opened our routing demo here. What we have here, and don't mind this configuration. We'll get to what that's about in a second. I have the configuration just right here in the application. You could have it in a separate file if you want to. I just did this for demo purposes. So we'll go and edit that in a minute. So the console application takes in that configuration that we saw earlier, that we'll go into in a minute. It creates a system called Elastic System in this case. We create a top-level actor called in this case, demo actor is the name of our actor, and is also the type of our actor here. We tell the demo actor to start, we tell it a new start demo message, and then we wait. So let's look at this demo actor and how it processes that start demo message. We've got our demo actor, inherits from receive actor. We've got some references here to what looks like a random number actor and our trusty console writer actor here as well. So here we are creating, as a child actor, it looks like, a random number after random time worker. So we'll look at what that actor does in a second. So in the constructor here of our demo actor, we're creating that. We're creating a random number actor called workers. And that's where our random number after random time workers are going to live. We also have our console writer actor. We're creating a child actor there and calling that console writer. So here, when we receive the start demo message, we're using another feature of Akka.net, which is the system scheduler. So what we're doing here is we're saying that we're getting the scheduler for Akka.net, and we're telling a message repeatedly. So we're saying, don't wait any time before you send the message, and then every 1 second, send a message to the random number actor. The message that we're going to send is a new generate random number message. So let's look at what that looks like. Well, first, let's look at the random number after. So basically, every second, a message is going into the mailbox of this random number after random time worker. So what does this look like? This random number after random time worker also has its own child console writer actor. Again, just demonstrating that we can have actors have their own children. We can have top-level actors. We can choose to utilize that console writer actor however we'd like. When this random number after random time worker receives a generate random number message, it writes something out to the console that says, I've been told to generate a number. It waits for between 1 and 10 seconds. Now, again, we're straight up calling thread.sleep here. right? So this is something that could be problematic, right? If you're doing async programming or if you're dealing with multi-threaded programming, right? I mean, calling thread.sleep could be a little problematic for that processor, but we're actually going to do that here, and we'll put the thread to sleep for the number of seconds that we generate, and we're going to generate a number between what, one and I don't even know, 1 and let's say 1 billion there. So a number between 1 and 1 billion, and then we're going to write out that number. And we're going to generate a random number after however many seconds. So let's go ahead and run this and just get a sense for how this is working right out of the gate. So the program is going to spit out that configuration that I have just for demo purposes. We can see here the one worker that's been sitting there. I've been told to generate a number. It's gone to sleep, generated this random number after 7 seconds, 2 seconds for the next one. But remember, in those 7 seconds, more messages are piling up in that actor's mailbox, right? So we're clearly not getting the throughput that we might want out of that actor. But luckily, with routing, we can actually do some things to make our system a little more elastic. So in our routing demo here, in this configuration, what we actually can do, first, let me do this. What we have here, first we have a single actor. Let's say we want more than one actor to process some things. So let's instead use a router. So in code here, I'm just going to, and again, I've redefined this variable. So imagine this is just me writing line number 2. I just did it so I could uncomment it quickly. Let's look at what happens instead if we create a router in code. So those props I told you, we have props.create the random number after a random time worker, but props have this nice property where you can create something with a router. So in this case, I can actually specify that when I create this actor, don't just create this actor, put a router in front of this actor. And in this case, we're just demonstrating, we're creating a new round-robin pool of actors, but with only one actor in it. So it's a group, but with only one actor in it. So how does that change how this program operates? We've created a router in front of this actor. We see here now workers /$A. So Akka created, we still have that /workers address where we can send messages, but it looks like there's a $A actor. Now that's something that was created by the system. Akka.net created that actor and named it $A. And so that we still have that one actor that's processing messages. So you can see still have messages queuing up there. So instead of that, why don't we instead create a round-robin pool with 5 actors, 5 instances that are created. So let's look at how that works. Now we can see A, B, C. We see that things are being processed a little more quickly, and we see there are 5 actors that have actually been processing messages. So we've got A, B, C, D, and E here. And they're all taking messages into their queue. That round-robin pool, what that's saying is, okay, every time a message comes into the router, right, evenly distributed round-robin style to all of those 5 actors that are in that pool. So they're each being, having those messages queue up, but now, of course, we're distributing it much across 5 actors instead of 1, and so we see we're getting a lot more throughput here. So lastly, so we could change, we could make that 5, we can make that 500, we can make it 25, however many actors we want. But the nice thing we can do is we can actually, rather than changing my code, I can say create a random number after random time worker with a router, and let's take that router from configuration. So now let's not modify our code at all. Assuming that I've published this, let's look at that configuration and see what we might do here. So here, I've got a section of configuration where I've commented it out, but I can say that if something sends a message to /demoactor/workers, use a round-robin pool, and I'll leave that commented for now. Use a round-robin pool and give me 25 instances of that thing. So now I've modified what's essentially a configuration file, right? If this was an external file, it would just be a configuration file. And I'm going to go ahead and run my program again. So it's going to pick up on that configuration that we've changed. It's going to see, you'll see here, A, B, C, D, E, F, G. It's going to go all the way down. Now we've got a round-robin pool of 25 actors that have been changed based on configuration. So one of the great things about this is when we think about how we want actors to be deployed or managed, or how we want to scale our systems, sometimes that's an operational concern. You'll note that if I wanted to 5 or 25 actors from this point on, I don't actually have to modify any code. To me, that is a huge benefit of Akka.NET, is the ability to have that, that sort of scalability concern addressed through configuration, rather than a need to restructure your entire application or put a queue in there or do something along those lines. We've actually gotten it to a point where we can handle that kind of change, that kind of structural change through configuration. Now, lastly, I saw something there that said it seems slower with more actors. Now, so just to be clear, what's happening here is it's not necessarily going to be slower. We're actually going to get higher throughput here. What's happening, let me just run it one more time, is every second a message is coming in, right? So we still have these 26 actors or 25 actors, but what's happening is now they're all able to process a message. Now, since this is happening at the random time, what you're actually getting is, if all of those were waiting for 10 seconds, it would seem a little slower, but you actually have the ability to process many more messages in parallel. So instead if I sent a message every 100 milliseconds, instead of every second, you would drastically see an increase here in throughput. So, and that's because those messages are being delivered and handled by a much broader pool of actors. So it may not seem like it necessarily depending on the timing, but you know, in fact, just for purposes of this, why not? Let's look at from time span, let's do time span from milliseconds, 100. So let's schedule that message every 100 milliseconds. We've got our 25 pool of actors. So rather than a message queuing up every 10th of a second in a mailbox, now you can see those messages are being processed by those actors. And if you're seeing some delay on the console output, by the way, that's likely because that console writer actor has been created on that thread that's been put to sleep. So that's probably more an effect of the demo than anything else. You can see here there's a huge amount of throughput there that just kind of cropped up. So my guess is that's actually based more on the limitations of how I structure that console writer actor than anything.
While you're taking questions, it looks like there's one more in the chat just above the address there.
Let me flip back to that. Is it more appropriate to have the volatile child stash and unstash its own messages, or to have the parent actor take care of that? That's a great question. So in this case, you don't necessarily need to follow that pattern for every time there's an issue, but what you might want to do is that child actors should have an understanding of what information is being processed. You can raise that in the exception to the parent actor and then allow it to decide what to do, or you can decide that that child actor is, understands enough to stash and unstash those messages, or to do whatever you need it to do. It may be that you don't want to reprocess that message. The key thing there is that it's really going to depend on what you need that actor to be doing, and what is the nature of that actor's work, and what kind of problems that actor might encounter. So I hate to give an "it depends" answer in this case, but what I want to mostly point out is that you can have that be the responsibility of the parent through what exceptions you raise and providing the parent actor with the appropriate information, or if you understand the child actor and you know that you're just going to restart it, the child actor can also say, when you're building the child actor there, you can say, okay, what needs to happen if this thing gets restarted? Well, if I've got a bunch of messages queued up, do I care about them? If so, I should probably stash them. So you can kind of, and if you're using Akka.persistence, you may not need that. If you're using event sourcing, there's going to be a different approach. So it's still a bit of an "it depends" situation there. I also have a question here: can a pool span across different machines? Great segue, Darcy, because in fact, the next thing we're going to show is exactly how we might do that. So in our so now we're taking this router from configuration. So what I've got here is I have an application here called Blank Slate. You'll notice a console app application. I've got some configuration here, so let's not worry about that just right away. So we've got some configuration. I've got an actor system that I'm creating. Now, in this case, I'm calling it Blank Slate. It's an actor system that's running in the console. It just says console.writeLine, sitting here doing my thing. Note, we haven't created any top-level actors. We haven't done any of that. in our configuration here for our blank slate console app that, again, is just going to sit there. It doesn't have any actors defined. It's not creating any top-level actors. What we have here is we have a configuration for remote. We say that this actor is going to listen on port 9001. In this case, it's going to listen on localhost. And so it'll listen on 9001, port 9001. Let's look at our demo actor program over here. Let's uncomment this line for remote. Now what we see here, well, first let me go ahead and just run this blank slate application just to show no tricks up my sleeve here. Let's go ahead and start an instance of that. Our blank slate, we can see here, starting remoting. We see that remoting is started. It's listening, so that's an Akka system message. And then we see it's remoting is now listening, but it just is sitting here doing my thing. No actors deployed, no work happening. So let's go ahead then, and I probably could have left that running. Let's leave that blank slate running here, and let's go ahead and start up our demo here, which is going to look and say for any demo actors, create a round robin pool of 25 instances and deploy them here to the blank slate actor system at localhost on port 9001. So start up our blank slate. Go ahead and show it here, sitting there doing my thing, not doing anything there. Let's go ahead and start up our routing application. Pull it over here. So it spits out that configuration again. And what you see here is this starting demo, but nothing is happening. And nothing is happening specifically because the blank slate actor in an entirely separate process with no actors running has had all of those 25 actors deployed to it by Akka.net and is now processing all of those messages in a separate process. And so what's one of the things that I think is key about thinking about Akka is that now with a configuration change, we've deployed actors to an entirely separate process. Now it's still a process on localhost. So that's pretty great though. Maybe you have some additional console work that you're doing, or you want to deploy something to a different process, or you've got some ways that you might want to deal with that. So let's think instead about how this might work across machine boundaries. Now recall earlier, I said no tricks up my sleeve. I had started an Ubuntu instance in the cloud, and I had gone and remoted into that, and I had installed .NET Core. So I'm going to go ahead here and just do some things real quick to see if I might be able to get this thing to work across machines. Now let's see if this is going to work. Well, you know, we'll play it by ear here. We'll see if it's going to work. So what we're going to have to do is we're going to have to go to find our. Let's go ahead. I'll go into the code directory here. This has got my code that I'm using. So you can see there's the hello world, the blank slate, et cetera, et cetera. So let's go ahead and cd into blank slate. And let's go ahead and edit. We'll edit that program here in Ubuntu, in Azure. By the way, using WSL to connect to it. Thank you, Microsoft, for WSL. Man, do I love that tool. So let's go ahead and let's look at what we need to do. So first thing I'm going to have to do here is I'm going to have to modify these network settings, right? So I'm going to go ahead and I'm going to paste in. First, I'm going to see if I actually captured this. If not, I'm going to open my Azure portal again and kick myself. So I'm going to go ahead and get the public IP address of this system. Do I actually have it? Let's see. All right. Just pulling it up on my other screen. Apologies for that. All right, I've got my public IP address there. I'm going to set the public host name here. Let's go ahead and insert that. And the private host name is going to be set to the private IP address, which I've got to figure out momentarily here. I'm going to pull that up in my VM. So typically I've done, let's see, so let's go ahead and private IP address. In this case is going to be, come over here, it's going to be 10. And so this is just a bit of networking configuration that you might do, right, if you're going to deploy it. 10.0.2.4 is the private IP address here. So I'm going to go ahead. I think I can go ahead and save that. Yes, I would like to save it. We'll keep it by that name. Okay. And now we're going to go ahead and build and run that. So let's go ahead and do .NET restore. So we're going to build that application here. So again, same source code that I pulled down for this demo. We just modified that file here. And we are on Linux running on Azure. It's a little bit of a slower instance, so I'm going to ask you to bear with me as the project builds. And while that happens, I'll just check to make sure there are no other questions happening here. None yet. So this is always the balance that I do of, okay, well, I deployed the Terraform, so we didn't have to wait for that. But I kind of wanted to show it at least building, so you didn't think I was bringing some pre-baked solution.
I have a question.
Sure.
Hey, it seems like, there is currently, it's not good for a scenario where you have to do like transactions and rollbacks and stuff. Is that accurate? Like the actor model in general?
Well, I think in general, if you're looking for like a call and response kind of situation, Akka does allow for that. But typically, one of the tenets that you're thinking about when you're building a system with the actor model is the idea of telling an actor to do something and then maybe waiting for a message to appear in your mailbox. The second you ask an actor to do something and wait for a response, you introduce a number of additional concerns. What instead we want to do is allow Akka to guarantee that the message is going to be received by the actor, and to tell you that to not throw an exception based on the reception of that message. And then once that happens, what we want to do is kind of allow it to do its processing. So in this scenario where you might be doing a transaction and dealing with an exception, what we have here is you may want to tell an actor to do something, have that actor process the transaction, and then when it's done, it's going to tell you that it's finished processing the transaction by telling you another message. Once you've received that message in your mailbox, you can react to it. Or if something goes wrong, say some kind of commit or rollback or something's happening, that actor might raise a specific exception to you, and then go ahead and you can handle that at the child actor level, the parent actor level, however that needs to be handled. But the key there is that we're sort of modeling our messages based on a tell sort of strategy versus an ask sort of strategy. Now, if you absolutely need that kind of guarantee, what Akka asks you to do is to put an upper bound on the amount of time you're willing to wait for a response there. And so, but typically as we're structuring actor-based applications, we want to rely more heavily on telling an actor to do something rather than asking it to do something and waiting on a response. Does that answer your question?
Yes, it does. Thank you.
Let's go ahead here and run we'll run .NET Run in our VM here, which again should just run our blank slate application. It's going to take it a second to go ahead and build that. And I have lost the meeting chat for some reason. So if you have other questions, feel free to mention. Oh, I came back. I see somebody asked for the GitHub link. That's great. All right, so now we see here that I am remoting is listening on in Ubuntu VM on Azure, running this .NET Core application, remoting, listening on this address here, right? And so now what I'm going to do is I'm going to go ahead and add that remote IP address here to my remoting demo. Let's go ahead and open my routing demo here in my configuration. You can see blank slate at localhost 9001. Instead, we're going to go ahead and paste that in there. It'll be at this remote IP address 9001. Let's go ahead and run that and see if my demo is going to be kind to me this evening. So we see here, starting the demo, right? So this is our console application sitting on our machine. Let's see how we're doing in our Ubuntu window. There we are. So this is a console application on my machine, now changing and deploying 25 actors into an actor system that is sitting on a remote VM in Azure running Linux. So cross-platform, cross network boundaries, across all of those things. And I changed that with 2 lines of configuration on my on the Linux VM and 1 line of configuration change in the configuration for my Windows console application. So I want to be clear about the power of this and the power that that sort of configuration and flexibility enables us to have. And so as we drop back to the demo here, just want to mention again that configuration is going to be a really powerful element. But you know, we've only just begun. In this case, we have thought, you know, Akka, as I mentioned, it has the idea of persistence. Right now, if the power was to go out while we were in the middle of this demo, all of those actors and their messages are being processed in memory, right? So it would all just kind of go away. That might be fine for some systems, and certainly if you don't need persistence, then you know no need to configure it. But Akka does have that persistence mechanism where you can utilize, as I mentioned, SQL Server, Cassandra, some other data stores to store the message before delivering it to the actor. And then if the power is to go out, when that actor sort of rehydrates itself, it's going to receive those messages into its mailbox. And so Akka's got some great systems to abstract that away for you as well. There's also the idea of clustering. So Akka, you know, we showed remoting, and Akka's clustering is sort of built on top of that remoting capability, where you can create groups of, you know, clusters that talk to each other, that know how to make the decisions, that know how to nominate a leader if one cluster node drops out, that knows how to separate different responsibilities and allow you to do that. And so there's some great functionality there as well. And lastly, there's also Akka streaming, where Akka.NET streaming, where say, oh, this is great, we're processing messages in parallel, but at some point we're going to saturate things, right? Well, Akka streaming allows you to kind of do some additional things, like say backing off when your CPU gets to a certain percentage, or backing off when your actors have X amount of messages in their mailbox, to make sure that you're not inundating the system or potentially overloading it. Just because you can, you know, put in 100,000 messages doesn't mean the system's going to be as responsive, right? You still have to handle that with actors. And so Akka Streams helps you work with that a little bit better. And so and there are other options as well. There's a specific package, I think, for finite state machines. There's an Akka texture project for event sourcing. If you really want to think about sort of domain-driven design and event sourcing on top of Akka.NET, there's another open source project out there that does that. And so as you think about this, and certainly if you're looking for more information, the #1 site for information on Akka is going to be getakka.net. That is going to be where we find reference to, I think, some of the boot camps, some great documentation and stories. It's also an open source project, right? So definitely feel free to roll up your sleeves and contribute. I've got the GitHub link there. It's a very welcoming community. They're always looking for help and folks to jump in and maintain the project. And lastly, of course, you can visit Petabridge for that boot camp that I talked about, or those paid training offerings. And there's also Roger's website as well, which is, I believe, nethouse.se. So open source is awesome. I hope you all get involved in that. Try this out, take it for a spin, wrap your brain around it, see if there's some things you might be able to make it do for you that you've had a little bit of trouble with, or where object-oriented programming alone hasn't necessarily been meeting your needs. I definitely encourage you to do that. And lastly, as we jump back over to some other questions, I'll leave my contact information up here just to make sure that we've got that available. I do hear some dings, so I will go ahead and jump back over to the chat at this point and see if I can answer some questions. Let's see. Are there any good places to find actor model-based architecture patterns? Yes, I think the Akka.NET website actually has some of those. There's that Petabridge site, which has, again, the bootcamp has some guides to modeling, and then there is even that full half or full day course on that. I think if you look at those introductory resources, that'll definitely give you the jumping off point you need to dive deeper on any patterns that interest you. And then the last question I see here is actors, or are actors, a microservice? And that's a great question. So microservices, I find, have a pretty fluid definition from time to time. What we think about as microservices, I would think about as a set of actors that have a specific purpose. So if I was building an Akka.NET cluster, my microservices might be workers with specific types of responsibilities within that cluster. In terms of how you're going to split that across domain boundaries, I think the typical rules of microservices still apply. If I had an area of my application that had a specific concern, I might split that into an Akka service or cluster that handled that concern and kept its data isolated, so on and so forth, from the other microservices that had a different boundary. And so I think Akka is a great tool to start with when you think about different responsibilities, because you can start to group those actors into the actor system that you're looking for, and then you can split that off into its own cluster if that looks like it's getting to be a little bit too expansive, or once your domain boundaries become a little bit clearer in that regard. So it's definitely, I wouldn't say it's a one-to-one of our actors and microservice. Actors are sort of an object pattern that can be used within this framework to enable a responsive application. And how you structure that at the overall service boundary, I think, is still going to be up to you. So that's my somewhat opinionated take on that. It's not the same thing, but they certainly can enable each other.
So thinking of this on scale, you, don't you have issues like the mailbox getting full, like running out of memory and stuff like that? Or
Sure.
It
So,
even seems like deadlock would be one of those issues with all these messages.
So in this case, deadlock's not going to be an issue, because remember, those messages are coming in one at a time on that event-driven thread. But what could happen, I mean, you are certainly receiving messages, right? So if each actor were to take 5 minutes to process a message that's coming in and was being inundated with messages, then there is the chance, right, that it could use up more memory than it should. So there are a couple ways that we avoid this. One is that messages you'll see are typically pretty small, right? They're immutable objects. They're containing maybe a string or a list or a couple of things. They're not really too heavy in terms of the objects that you're using, right? We try to keep those messages pretty sparse. We're not serializing a giant something over the wire, right? We definitely want to avoid that sort of thing. So when we think about messages and their immutability, right, we're keeping those messages fairly small. So that's tip number one. Tip number two is going to be that as we think about that and as we structure our actors, remember that actors are designed to push volatile or dangerous work down further in the hierarchy. So if you are an actor and you're doing something that takes 5 minutes, that's probably a task that could be deconstructed, right? And the goal here would be to deconstruct that work, push that into child actors, or come up with a message flow that makes sense for that sort of unit of work to be completed. And so that's following those various patterns, or fanning out, or an actor per entity, or something along those lines where you're able to process those things in a heavy throughput. So if you've done that and your actors are processing messages fairly rapidly, but the volume of the system is still growing to such a point where your actors might become unresponsive, couple things you can do. You could use the Akka streams, right, to sort of back off on the delivery of new messages to the mailbox. Now, that might mean that some messages get rejected. You could also scale up, right, more cores, more RAM on a single machine if you wanted to play it that way. You could also scale out and turn that one machine into a cluster that now can share the burden of those messages, and Akka makes it very friendly to do that. And so those are certainly concerns as you hit the upper bounds of what the system's performance can be, but Akka has a number of tools in the toolbox to mitigate those concerns. And I would posit that it is able to do that better than we would be able to do so without it as a framework.
Thanks.
I have a question about the mechanism by which messages are delivered. Is it are they delivered at least once or exactly once? In other words, can it be? Do I have to write my code to be idempotent in the sense that I have to make sure I've already handled that message?
Messages, I believe messages in Akka by default are at least once delivery. So we do have to take that into account. There are some systems that are some mechanisms that you can put in place to guarantee, I think, at most once delivery. I think the guarantee of exactly once delivery due to network constraints is a little bit difficult. I may be remembering that backwards, but I'm fairly certain it's at least once delivery by default, and there are other mechanisms that you can put in place, though there's going to be a performance hit when you do that, because Akka's got to do some additional understanding and processing behind the scenes. So if that's a key consideration for a part of your application, Akka.net allows you to do that, but you're probably going to have to take a small performance hit in order to accomplish it.
Okay, thanks. And one more question comes to mind. Is there any tooling that deals with system health, just knowing whether a given entity on a cluster is up, is alive, am I having issues with it?
Sure. So there's actually, this is one of the key plays of Petabridge in this market. So in addition to helping folks implement Akka.NET, right, one of the commercial offerings that Petabridge has is a tool called Phobos. So if you're operating Akka.NET at, in sort of an enterprise environment, you're making a legitimate investment in it. There's some very decently priced tooling that allow you to do exactly that. Create really nice graphs, surface alerts. There's also petabridge.command, which I think is free, that will allow you to query the state of an actor, send commands to an actor system, get some information along those lines. I got to double check myself on whether that's a free tool or not. I haven't looked at the Petabridge offerings in a little while. So in short, you definitely can write your own to do it. There are commercial offerings that will do it. I do not know if there's any free option to do that reasonably well at this point. And if you're operating in an enterprise environment, Petabridge makes it pretty easy to adopt their tooling in terms of their pricing and licensing and whatnot. So I think the shops that tend to be investing in Akka.NET or in the actor model in that way will find value from that tooling enough that they'll typically purchase it.
Awesome, thanks.
Scanning the chat, I don't see any other questions at this point. So what I'll do is I will say certainly thank you for joining. Thanks for taking time out of your day to learn a little bit about the actor model in Akka.NET. I'm available if you want to catch up or you want to talk about this. You can find me at those places online, and happy to. I saw someone posted the link to the repository, and I'll make sure that I post a link again to the slides here and the repository link as well. So thanks very much for having me, and it's been great to talk with you.
Thanks, Sean.
Thank you, Sean. This was fantastic.
Excellent. Well, happy to be here. So I hope you all have a great evening, and we'll talk to you soon.
All right. Take care. Bye.
Great. Thanks. Bye-bye.